Hello everyone. Today we're going to learn some basic thermodynamics with calorimetry, particularly the kind that you learn in physics class. We will be going over thermal properties like specific heat capacity, phase changes and latent heat, and how to calculate the final temperature of objects that start out at different temperatures and end up in thermal equilibrium. The first subject we talk about is specific heat capacity. You might notice that different substances, like metal versus water, will heat up at different rates. That's because metal has a very low heat capacity. It takes a small amount of heat to raise its temperature, whereas water has a high heat capacity. It takes a lot of heat energy to raise the temperature of water. So there's two related concepts. One is heat capacity, the other is specific heat capacity. Heat capacity without the specific has to do with particular objects. Like this eraser has a heat capacity. Specific heat capacity has to do with the substances that it's made of. The rubber in this eraser has a specific heat capacity. The object eraser has a heat capacity. The material it's made of has a specific heat capacity. For any material, I guess I gave the answers here. Let's just pretend those are covered the whole time. For any particular material, the specific heat capacity is the amount of heat it takes to raise 1 kilogram 1 degree Celsius, or 1 Kelvin. So this here is the definition of specific heat capacity, but these values of specific heat capacity for each material can be measured in the lab. They're known, and we can look them up. Therefore, it's more useful to write the equation this way. We want to know the amount of heat in joules it will take to raise a certain amount of the substance by a certain temperature. If you're a physics student, I highly recommend keeping a note sheet devoted solely to the important equations that you can just pull out whenever you're doing homework. And when I'm tutoring, I always box the important equations in green. I've taken to calling them green box equations. Whenever I box an equation in green, it means add that to your equation sheet. The specific heat capacity is oftentimes shortened to specific heat, so I will be calling it that from now on. The specific heat for a given substance is constant, so we can measure it in the lab and write it in a table, and look it up in a table when you're doing homework. For water, it's 4,184 joules per kilogram per Kelvin. For ice, it's about half that. And you could use Kelvin or degrees Celsius here, and the number won't change because the size of each unit is the same. If you want to convert between Celsius and Kelvin, just add 273.15. Subtract. If you want to convert between Celsius and Kelvin, subtract 273.15 from the Kelvin temperature. The Kelvin scale is the Celsius scale, but with 0 at absolute 0. Absolute 0 being the temperature at which all molecular motion stops, the coldest possible temperature in the universe. All right, let's do an example problem. How much heat does it take to raise 20 grams of ice from negative 13 degrees Celsius to negative 8 degrees Celsius? So to do this, we use the equation we just learned. Heat equals mass times specific heat times change in temperature. So this is a pretty simple one. We just plug in the numbers. That's the mass we're given. That's the specific heat for ice, as you can see right up here. And this is the change in temperature. So it's going between negative temperatures. So it starts at negative 13. So remember a delta anything, in this case temperature, is equal to the final minus the initial. It's the difference. It's what the change is. So here we have the final temperature, negative 8 degrees, and then the initial temperature, negative 13 degrees. And they're negative, and we're subtracting them, so we get a double negative here. When you're writing it on your homework, you don't have to do the double negative. You could just switch the order of the numbers. So then we calculate, and we get an answer. 210 joules. And we can use Celsius. We don't have to convert to Kelvin because the difference in Celsius is the same as the difference in Kelvin. It's just the absolute values that are different. All right, so I have another question out here. How much heat does 15 kilograms of water give off when its temperature lowers from 36 degrees to 11 degrees? And instead of solving this one here, I'm going to let you guys solve this one. Let me know your answer in the comments. We'll see who gets it right. There's the specific heats for water and ice for your convenience. Moving on, latent heat. So not only does heat energy raise and lower temperatures, it also changes substances' phases. So when ice reaches melting temperature, it doesn't just melt all at once, it takes energy to melt that ice. And that energy is called latent heat. And again, I just kind of gave away the answers. We'll just leave it for now. The definition of latent heat is the heat it takes to change a substance's phase divided by the mass of the substance in question. And the way that you usually see this equation is this way. Because again, latent heat is something you look up in a table. You use the equation, heat is equal to mass times latent heat. That is the heat required to, for instance, melt m mass worth of ice. Latent heat is a constant for a given substance's phase change. LF is called the latent heat of fusion. It can also be the latent heat of melting, but we call it of fusion because it's the same either way. It's just one is positive, one is negative. That's when a substance melts from solid to liquid or freezes from liquid to solid. The other type is LV, the latent heat of vaporization. That is when a liquid vaporizes into gas or a gas condenses into liquid. For water, the latent heat of fusion is 334 kilojoules per kilogram. You notice this is kilojoules. That means it takes a lot more energy to melt a gram of ice into water than it does to raise a gram of ice by 1 degree. Another example is the latent heat of fusion of nitrogen. If you've heard of liquid nitrogen, it can also become solid, and that's 25.8 kilojoules per kilogram. All right, so an example problem. How much heat does it take to melt 45 grams of ice, which starts at minus 11 degrees Celsius? So in this case, we have ice that starts below freezing. We have to raise it to freezing temperature, and then we have to melt it. So the heat is equal to Q, what does that even say? Q heat, I think, plus Q melt. So the heat required to raise the temperature plus the heat required to melt the ice. That is, if we put in the formulas for that, we get what we had before, mass times specific heat times the change in temperature, plus mass times the latent heat of fusion. So the next we put the numbers in, there's the mass, we have our specific heat of water times the change in degrees, so it goes from minus 11 to 0. The change in temperature is 11 degrees, plus the other term, which is the mass again, plus the 334,000 joules. You know, K means kilo, kilo means thousand. You know, we sometimes think of K as meaning 1,000. If you have 5K of something, you have 5,000 of that. That comes from the metric system. So anytime you see K here, you can translate into 1,000. All right, then doing all that math, and we get 16,000 joules. Okay, now thermal equilibrium. This is a phenomenon that comes about when two substances at different temperatures come into contact with each other, and heat flows from the warmer object to the cooler object until they both end up at the same temperature. So when two substances beginning at different temperatures exchange heat and end up at a temperature in the middle. A calorimeter is a device used in experiments as a container in which we can measure the heat transferred during this process. It's designed of an extremely high heat capacity material which allows as little heat as possible to leave the system. So we can approximate that no heat leaves the system and no heat comes in from outside. So it's a way to isolate the experiment so we're not losing information. And I will probably paste a picture from Google Images over this because I'm sure you cannot tell what it is from the diagram I drew. Okay, here's an example. 20 grams of copper at 90 degrees. I didn't write the degree symbols. I can't really type the degree symbols here, or at least I haven't tried hard enough to figure it out. There we go. 20 grams of copper at 90 degrees Celsius is dropped into a calorimeter containing 2 kilograms of water at 20 degrees Celsius. After a long time has passed, what temperature are the copper and water? So the key words here are after a long time has passed. This suggests we're looking at thermal equilibrium. So what we know is that as they change temperature, the heat coming from the copper goes into the water. Mathematically, we can write that like this. The heat of the water equals minus the heat of the copper. So then we set up our equations. It goes mass of water times specific heat of water times the final temperature minus the initial temperature of the water, delta T for the water, is equal to minus, got the minus sign, that's important, the mass of the copper times the specific heat of copper times the final temperature minus the original temperature of the copper. You might think, why is there a minus sign? That doesn't make much sense. If one side is positive and the other is negative, how can that be real? The answer is that the copper is cooling down. So its final temperature is going to be lower than its initial temperature. Why do I have such thin lines? So that means this here, this difference is negative, and it accounts for the negative out front. So we need to find the final temperature, and it's on this side and it's on that side, and it's in parentheses on both sides, which means this is going to take some algebra. But that's okay. We're in a physics class, which means we love algebra. So the first step is to distribute the parentheses. So I've taken the mass and the heat capacity and distributed it to both of the temperatures on both sides. Next, we want to get the terms with our final temperature we're looking for on the same side. You know, I should have highlighted these as different color. There we are. I don't know why I didn't think of that before. I think I might do this from now on. So we get all the terms with the desired variable on one side and all the other terms on the other side. After that, we factor out temperature final and divide what's left to the other side. I guess I left out a step of the algebra. But essentially, we factor out the T final and then divide these terms inside parentheses to the other side. So this is the final relation for this particular problem. Now I want to point out something very important. Do not memorize this. Do not memorize the final step, because this is something that is specific to this particular problem. If you memorize this, you can do this exact problem with different numbers, but you can't do similar problems. What you want to memorize is the process, where to start. Heat from the hot object flows into the cold object. This is what you do. The heat from the water is equal to minus the heat of the copper, because the copper is the hot object and the water is the cold object. Everything else flows naturally from here. And I didn't calculate this because the important part is showing this process, not really what the answer is. So if you want to do the answer for yourself, you're welcome to it. From here, it's just plugging into the calculator and getting a number. All right, putting it all together. Now we're going for the most complex problem of this type that you will find in the entire class. Thermal equilibrium with a phase change. Suppose 15 grams of ice at minus 12 degrees is placed in 1.5 kilograms of water at 6 degrees Celsius. What is the final temperature of the solution? I don't know if it's technically called a solution. I'm a physics guy, not a chemistry guy. Sorry if I offended anybody by getting it wrong. So the important thing to know about this is we have two objects that are the same substance but in different phases. And so there are three possible final temperatures we could get, three possible scenarios. One is that the ice rises up to melting temperature and the water cools down to freezing temperature, which are, of course, the same temperature. Once both substances reach freezing temperature, no more heat is exchanged because they're at the same temperature, regardless of whether the water started to freeze or the ice began to melt. In that case, the final temperature is 0 degrees. The next possibility is the ice goes all the way to melting, but during that amount of heat, the water only goes a portion of the way to freezing. Then the ice melts, and during that time, the water still only goes a portion of the remaining way to freezing. Then the water that used to be the ice continues to warm up while the rest of the water continues to cool down, and they meet at a temperature above freezing. And the last scenario is the reverse of what we just talked about. The water cools down to freezing, it freezes all the way, and then it continues to cool down more as the ice rises from -12 toward the water and meets the ice that used to be water somewhere in the middle. So to solve this problem, we have to start ruling out these scenarios. And the way we do this is step 1, we calculate the heat needed for the ice to reach melting temperature and the water to reach freezing temperature. And the smallest of these values we call Q1. That is the heat during the first stage of this process. So the heat required to raise the ice is mass times specific heat times the change in temperature, of course, which we plug in the numbers, and we get a value of 376.74 joules. For the water, it's the same equation. Of course, it's minus because the water is cooling down. We put the numbers in. Specific heat of water, mass of water, 6-degree temperature difference. And I took care of the minus sign by having this be a positive 6 degrees instead of a negative 6 degrees. What I mean is I canceled out the double negative sign. So therefore, the heat the water loses is 37,656 joules. With our results, the heat needed to warm the ice is less than the heat needed to cool the water, which means the ice reaches a freezing temperature before the water. And we have a diagram here that shows us during this first 376.74 joules, the ice heats up to 0 degrees, the water cools down to some temperature, we don't know what it is. Now we don't have to calculate this temperature, and you'll see why in a minute. Step 2, we have to calculate the heat needed for the ice to melt, that is the heat during this phase, and compare it to the remaining heat needed to bring the water to freezing. So we will be comparing this amount of heat with this amount of heat. It really wants to go to the numbers. So you get what I mean. Let me just leave those up there so that you can see what we're comparing. So the green is what we already calculated, stage 1. Blue is what we're comparing in stage 2. So the heat to melt the ice, I'm going to call Qm, is equal to the mass of the ice times the latent heat of fusion of water. And we put the numbers in, 334,000, which we saw on a previous page, and the number for this is 5,010 joules. If we add that to the heat of ice we calculated in step 1, 376, we get 5,386 joules, which is still less than the heat required to make water go down to freezing temperature. Remember, that was 37,000 joules. So what this means is that the ice melts before the water reaches freezing temperature. So in step 1, we discovered that the ice reaches 0 degrees before the water reaches 0 degrees. In this step, we discovered that the ice fully melts before the water reaches 0 degrees. So our final temperature is going to be somewhere above freezing. So here's the diagram for that. Here's the diagram of what we have so far. Step 3, we discard Q water because we know the water is not going to reach all the way to freezing temperature. So that number was only used for comparisons. We have compared it completely. We don't need it anymore. So now we can put together the final equation with step 4 to calculate the final temperature of the water. So on the left side, we have the heat to warm the ice plus the heat to melt the ice plus the heat of the ice warming after it is turned into water. And on the right side, we have the heat lost by the water. Again, just as before, this is Q ice total is equal to minus Q water total. So there's a couple details worth noting here. We have mass of ice here. Even though it's transformed into water, we're still looking at the same quantity that used to be ice. So that's why we use the mass of ice, but the specific heat of water. And our delta T is the final temperature minus 0 degrees because this ice is water at 0 degrees. So the portion of time that the matter that used to be ice is warming as water starts at 0 degrees. So Q ice is minus 12 to 0, Q melting is 0 to 0, and this final step is 0 to whatever the final temperature is. On the right, we have the net amount of heat lost by the water, which is something like this. And here's our final equilibrium temperature. All right, from here, the algebra is basically the same as with the previous example we looked at. We can put in numbers for Q ice and Q melt because we've already calculated those up here. But other than that, again, you're rearranging the equation to solve for temperature final. Let's just replace those with green again. You're solving to find for temperature final, like we did with the previous problem. The algebra is going to be about the same. The 0 degrees is nice because that means you don't have to do anything with that. And that is calorimetry in physics. That is thermal equilibrium without any heat lost or gained from the environment. We looked at the specific heat capacity, which is the amount of energy it takes to raise a substance's temperature. We looked at the latent heat of a phase change. It's the amount of heat required to change a substance's phase from solid to liquid or backwards, from liquid to gas or backwards. And we looked at a couple thermal equilibrium problems. We talked about a calorimeter as an experimental device to prevent heat from leaving the experiment or coming into the experiment. We did some sample problems involving a warm object and a cool object put together and exchanging heat coming to equilibrium. Lastly, we did an equilibrium problem where phase changes were involved. Our first step was to find out whether our piece of ice reached melting temperature first or the water reached freezing temperature first. There were three possibilities. Either both substances reached freezing temperature and the answer was 0 degrees, or the water got to freezing temperature, completely froze before the ice got to melting temperature, in which case the equilibrium temperature would be below 0 degrees. Or the third option, the ice could rise to melting temperature, melt completely, and then meet the water at some equilibrium temperature above freezing. To figure out which scenario it was, we started by calculating the heat needed for the ice and water to reach that freezing temperature, and compared them to find out which one actually did. After we found out that the ice reached melting temperature before the water, we calculated the heat necessary to melt the ice to compare that to the remaining heat needed to bring the water to freezing, and found out that all of the ice melted before the water got to freezing. So finally we had our equation, 3 steps for the ice and 1 step for the water, and we could solve for the final temperature and find our answer. That's it for today. Thank you for watching. If you're taking a physics class or you know someone who's taking a physics class and you want a tutor, you can sign up for my website at physicstutorchris.com. If you like what I do on YouTube, you can subscribe to the channel, like the video, and share it with others. And if you think free educational content like this is valuable, you can support me on Patreon at patreon.com/ChristianDHorst. You'll be supporting both this channel and my science and sci-fi channel, and your name will appear in the credits of both channels like these cool people. Thanks again for watching. Happy studying.